single roots. Okay. And this is the height of the element in Q plus. And the P is the Weyl lattice, and P star is dual Weyl lattice. And W is Weyl loop. Okay. And UQG is usual quantum algebra generated by EI, FI, and Q to the H. Okay. And UQ minus G is the subalgebra, negative subalgebra generated by FIs, and UQ plus G is the unipotent plus subalgebra generated by EIs. Okay. Okay. So first I introduce the quantum shuffle algebras and the quantum coordinate ring. Quantum shuffle algebra F star is an associative Q algebra generated by F star nu. Here nu is the multi-index. Sorry, I is the index set of simple roots. Okay. This is the index of thinking diagram. Okay, so this is generated by such ones. The product is defined by so-called shuffle lemma. This is the shuffle lemma. Okay. It's really complicated, so I don't need to say exactly, but I introduce it here. Here we prepared multi-indexes, mu star, and mu double, so mu prime and mu double prime. The product is defined by these formulas. Here the S M L is so-called shuffle. Let's keep the order ML, so it's ML is like this. So still keep the order because we just separated here. This is shuffle lemma, then their product is defined like this. Okay. And the important quantum coordinate ring a Q of n is defined as a restricted dual of UQ plus. Okay. The form is like this. And as it is well known that there exists an embedding of algebra, a Q of n is embedded in F quantum shuffle algebra. Okay. So Fi sends to Fi star. Here a Q n is generated by this single Fi is a single index, and then Z form is also defined like this. Okay, this is a quantum coordinate ring. Indeed, this is isomorphic to UQ minus. Okay. And now I introduce the crystal case of UQ minus. So define the Casual operator on UQ minus. Here, every element in UQ minus can be written uniquely in this form. Here, we fix some index I. Okay. Then, so every element in UQ minus can be expressed in this form. Here, what is UK? UK is coming from here. So K, I do have to define the EI prime, but the EI prime is some, how to say, kind of Q boson algebras generator. Then so it's like how to say, U is U. Then there are many strings in UQ minus. It's just this is the kernel of EIs. Then U is the linear combination of these vectors. This length is this K. U0, U0 is U1, U2, and so on. These differences just then the Casual operator is defined. Here tilde just shift this exponent to K from K to K minus 1, and Fi tilde sends K to K plus 1. Okay, this is the Casual operator. Then using this, we define first L of infinity. L of infinity is applying all the summation of all these vectors inside UQ minus. Here, U infinity is just unit of UQ minus. And the B of infinity is an element in this form, and this is a subset of this quotient space. So infinity over QL infinity. Okay. And the value epsilon I and phi is defined like this. And so Kashwara shown that we can recover UQ minus from L of infinity by extending the coefficient. And the B of infinity is a Q basis of this quotient space. So this means we just send Q goes to 0, then so it calls Fisher basis. And the Kashwara operator acts on this quotient space. But the remarkable property is the subset. This is the basis. The basis is also preserved by the I tilde and the Fi tilde. This is a set, not vector space. But still it's preserved by the action of the I tilde and the Fi tildes. This is the remarkable property of vector basis. And also I tilde and the Fi tilde are almost inverse each other. If it doesn't go to 0, we cannot go back. But if it doesn't go to 0, so we can go back here tilde, tilde. Okay. So the crystals. A crystal is a combinatorial object obtained by abstracting the properties of crystal bases. So indeed, it's a 6-tuple B, Weyl, epsilon, phi, epsilon, phi, I tilde, Fi tilde. It's a crystal. If B is a set, just a set, and there exists some extra element 0, but 0 is outside B. Okay. Then so these weights has such properties. It's too much, but important is the number 4. So it says I tilde FHs are almost inverse each other if it doesn't go to 0. So it's coming from okay. Then by this property number 4, we have a graph structure on crystals. It is called crystal graph. How to make them? It is oriented I-colored graph. Here, ROI is really obtained by Fi tilde. If we have a Fi tilde from B to B prime, so we just do ROI. Then we have the graph structure on set B. Okay. Then this is the example. For I, we fix I, some index I. And set BI is like this. As I said, this is same as the set of integers, just each vector parameterized by integer n. But their weight is n alpha. Alpha is a simple root, I is simple root. And epsilon I and I is minus n, like this, and then, but if I and j are different, so epsilon j and phi j, we take minus infinity. And I tilde act on ni is just to n plus 1, and Fi tilde sends n to n minus 1. And I, j are different, so it goes to 0. 0 is outside B. Okay. Then the crystal graph of Bi is like this. Because if I and j different, so there is no arrow because it goes to 0. So only ROI appear in this graph. So 1 goes to 0 by I, 0 goes to minus 1 by I, and so on. It's infinitely long sequence graph. This is example. And then also this is important example for today's talk. Okay. Because we consider the tensor product of these crystals. Its structure is as follows, but it's a little complicated, so I don't want to say so much. But anyway, so tensor product. So generally, crystal basis has a tensor product structure. But I do not give the exact definition today, but only concentrate on this one. Okay. So and as I said, tensor product. This is a set. So tensor product is not defined so generally, but as I said, the tensor product means the direct product of these sets. Okay. And then so now we take using these notations x1, xm, it means this so 0, 0, 0. So applying fis and that one. So this means like this. Okay. And we define the function sigma k like this. Let's take k, and then before we just take before entries, but multiplying these cardinal entries. And sigma tilde I is the maximum of this value. Okay. And m tilde I is the k index. It gives the high, maximum value. So it's like m is a sigma is a function. It's like this. Sorry. It's no good example. It's like so the maximum is here. Then mi tilde is this. And the small m tilde fi is the maximum of mi tilde, capital Mi tilde. So this one is here. And small m tilde ei is the minimum. So this is this one. Okay. This graph is. Then so these value just define the action of the tilde, fi tilde on the vectors as follows. Okay, so if I tilde act on x, then kth entry just shift by 1 or 0. Only unique place, this part just increase by 1. And ei tilde sends x, each x k 0 plus 0 or plus minus 1. So minus 1 is only this place. Okay. And the weight and the epsilon is defined like this. So then this gives the crystal structure on tensor product of the i's. Okay, then so now introduce the function delta k. Here we fix the sequence of indices I1 and so on In, and take k among here. Then what is k plus? K plus is the next index which gives the same index ik equal il. If not, so we take this is k plus m plus. Then the beta k is defined as just the difference of sigma k's, like this. So we have the beta k in this form. Okay, and then small m tilde fi and small m tilde ei are determined by beta k's. So because the important is the differences between neighboring part. Then now introduce the for embedding and cohedral realization. So it's really complicated. So today I only need here this blue part. B of infinity, this is the crystal base of UQ minus, can be embedded in Z-lines, finite rank Z-lines. And we take here I is the reduced longest word of variable element. Here the capital N is the length of W naught. W naught is the longest element in while group. Of course, in general category settings, we cannot take N infinite. It should be infinite. But this today's setting is finite, simple or simple situation. So we can take N in the finite, N in the finite numbers. Okay. But this is embedding. So we need to obtain the exact image of this embedding. So this is obtained by so-called polyhedral realization methods, but today I don't need it. But some example here. So A2 case, we take I is 1 to 1. This is the longest reduced word of A2 case. Then we need 3 coordinates, x, y, z. And they satisfy this inequality. So this gives really B of infinity. Exactly. But today's talk is just we consider the reverse. I mean, we obtain from here to here. But today we go back from here to here. This is the, how to say, localization process. Okay, so we go to next. Then, so this crystals tensor product of this one. Between them, we have a so-called braid type isomorphism. So the cartan data satisfy these conditions. So finite case just cover all cases. Okay, ij, aij, ji, 0, 1, 2, 3 cases. So we have these 4 type isomorphisms. This means all for any reduced word, so this crystal are isomorphic each other. Okay, so I rewrite in habit. So then we call this crystal cellular crystal. But it's not related to cellular basis, so it's confusing. So, why I call this cellular crystal? Because this crystal is a product, and I is a reduced word. It is obtained by considering the tropicalization from the positive geometric crystal on some Lagrange dual sugar cells. Then so we call this as cellular crystals, but I'm not sure that the name or not. Anyway, so this crystal has a following remarkable property. So as a crystal graph structure, it has a graph structure, but then this graph is connected. Means each vector is connected by arrows. Okay. But this fact, unfortunately, I don't need today. But the proof for this theorem is important for today's talk. Okay. So now I introduce the subspace Hi. So just remember the beta k, that's the difference of sigma k's. The express form is like this. Then now we consider the system of linear equations, beta k or beta k is 0. The solution space, Hi, inside Bi, this is vector is from the n into the n. This is a subset. This has also some good property. Indeed, if we define Hik is this formula I here, so I capital bold I is the reduced longest word, the variable element, and Hik define this formula, and bold I is this vector using this. Then these Hi's are the basis of this solution space. So please remember this part. Example for G2 case, the Cartan matrix, and reducing on this word is 1 to 1 to 1 to 6. Length is 6. Then we consider the 4, B1, B2, B3, beta 3, beta 4. Beta 5, beta 6 is we don't need because 5 plus and 6 plus is outside. 1 from 1 to 6. Okay. Then the express form of H1 and 2 is coming, it's obtained by this formula. Is really in this form. Then this is a Z basis or Z basis of H1. Okay, this is example, which is case. So now we consider the following lemma. First, BH of infinity is just a subset of BI. BI is as I wrote I1, okay, BIN, this is B beta, BI. And B infinity is realized here. As I said, this is partial embedding. And then we consider the shift B infinity by H. H is coming from this space. This is a solution space of the case. Okay, so then here is B infinity. And then so just shift by H. This is BH of infinity. Then so we take H so many. Then so there are many BH. So we change H like this. So just from B infinity, so we just shift many things. The important fact is that so this shift and operation EI tilde where tilde can commute. So it's really practice. Okay, it's important. So then all vectors just move at the same time, not only the highest. So the action is just compatible with these shifts. Okay. And also B infinity and the BH infinity has always intersections. No, not empty. And finally, so we consider the all union or union of these things. This recovers BI. Okay. So it's just to go back from BH and the shift, and then consider the union. So this recover BI again. This fact is important for today's talk. Okay, so next. Yeah, now so I changed the subject. So I just explained the crystal basis. And next subject is quiver Hecke algebras. So take field I and finite index I, and we take some polynomials in U and V to variable polynomial Qi, J, UV. It satisfies the following conditions, some symmetries, and the Qi is 0. And plus some other conditions, but I omit that one, so today I don't need it. Anyway, so we prepare set I, field K, and polynomials. Then we define the quiver Hecke algebra, so or it's called K and R algebras, but today I call this quiver Hecke algebras. Beta is from here. Okay, so the generator is like this. This one, and these 3 types generators. First one is just like idempotent because their basic relations is here. Total summation is the unit, and their properties is just usual properties. And xk is the commutative generators. So, and the tau I is like generator of Hecke algebras or simple reflections of Weyl groups. But the relation, and then Q appears in next page here. Q is here or here. Anyway, so yeah. Anyway, so these are basic relations. And it has also grading. The relation above here are homogeneous if we define their degree like this. Then our beta becomes a Z-graded algebra. Here we define the weight of our beta modules M as weight M is minus beta. But here the graded algebras, we consider the module is also graded modules. So good points, so this algebra is in general, we consider the total summation of this one. This is infinite-dimensional algebras. So, but if we consider graded algebras and graded modules, so we can apply finite-dimensional algebras theory can apply to here. So that's the good points. Even R is infinite-dimensional, but we can apply many results, theories from the finite-dimensional algebras. So this is a good point for graded modules and graded algebras. Okay. So each one is finite. Okay, so next we consider the R modules. First we introduce grading shift functor Q. So the graded module has such decomposition. Then Q is just shift degrading. And now we consider the convolution product of modules. Here, this it's not good notation. So circle, usually circle means convolution, but here I mean this is convolution product. So but I follow the Kashiwara's notation, so I cannot avoid that. Anyway, so this is tensor product, usual tensor product of K, and then so we just reduce up like this. This is a convolution product. And then here is a head, and so for this introduced by the head is the so this nabla is the head of this convolution, and delta is the so-called of this product, convolution product. Okay. And we call our module M is real if we consider the M circle. M is also simple, so we call M is real. Of course, if not, we call it imaginary. But today I don't need imaginary modules, we only need real modules. And if M is isomorphic to M star, so we call it self-dual. The categorification of UQ minus and the AQN. So we consider the two categories. Our beta Gmod is a category of finite-dimensional graded R beta modules. And our beta G project, the category of finite-generated graded projective R beta modules. Okay, so these categories are monoidal categories by the convolution product. Then this is very famous important result by Lauda and Hecke. So K-rgmod or respectively K-rg project, either can be ring of monoidal category, these categories. Then obtain, so the project is categorified UQ minus Z is Z form. And rgmod categorified AQN. Today we need this part. So we only, after here, so we only consider rgmod only. We don't have to consider the rg project. Okay, now we define two functors, EI and FI. It's from R beta G mod to RG beta minus alpha I G mod by applying this projection on M. EI alpha I beta minus alpha I defined by this formula. And FI is just we consider the conversion product Li and M. So Li is one-dimensional simple alpha and modules. Okay, so this is functors. And then, so fortunately, so for example, this is satisfy these conditions, so this is the so-called Q-boson relations. Then, so this categorified this one. Okay. Then also Lauda and Vazirani obtained the following results. They categorified the B of infinity. This is crystal. They categorified the B of infinity by the following way. So here we take so a simple module M, rgmod. They defined like this: weight, epsilon, phi, and the EI tilde on M is like this. Here we consider EI. EI is already defined here. Then taking circle and then shift like this by Q, or it's isomorphic to head of EI M to the Q. It is shifted by Q like this. And if I tilde also take the head of FIM. Then so B rgmod is the family of self-dual simple modules. Then so they show that this one has a crystal structure and it is isomorphic to B of infinity. So in this sense, so this is the categorification of B of infinity. So we need these results. And next, I changed the real. So now I explained the. Sorry, it's too late. Sorry, I should be localizations. So consider the molecular category T. One is a unit, and by factor tensor product or convolution product is here. So Q is a gradient shift. What is graded grader is a triple C, RC, phi. C is the object, and phi is a function, Z linear Z value function. And R is just flip C conversion X to X conversion C with some gradient shift. Why we use R is it's like R matrix. So using R here. They satisfy some commutative diagrams, but so this is like a kind of associativity. So next we consider another lattice, gamma and gamma plus. So right now it will be weight lattice, and gamma plus will be dominant weights. Okay, so what is the real commuting family of graders in T? So this is, so Ci is some subject object, and then so phi I satisfies this. This is a function. Satisfy these conditions, and RCI CI is just the scalar. CI product CI sends to CI to CI is a scalar, and also this convolution. So this is not, so it's very confusing notation. So this is just the convolution of these R matrices is also scalar. Then so Kashwara and the operator show that, so suppose we have a real commuting family, we can choose the bilinear form family map H such that this one, then they resist the C alpha. Alpha is coming from this set. And also there exists isomorphism between this one. So this means, so Ci is a basic object, then we can accumulate them according to gamma plus. So we have such subject. So this is important part. Okay. Then now we define the localization. So here we take the real commuting family here. And then so we need now define the partial order on gamma. It is usual order on weights. Then define the subset in gamma D alpha 1, alpha 2, and so on is like this. Then now we consider the two objects direct product object T times gamma and delta T. So their morphism is defined like this. It's really complicated. So, but then an important point is for delta and delta prime. So delta is smaller than delta prime. So there exists such map from here to here. And finally, so this makes the inductive system on this order. This one. Then finally, so it means we have an inductive limit of these systems. Then so it gives us the localizations. Okay, so what is the localization of category T? Object is obtained by the product object T times gamma. This is object. And morphism is just the inductive limit of this one. Okay, so this is, but it's really complicated. So the important point is following properties, and that's all we don't need in tilde and or like this.
If I may ask, how is this related to like other localizations, like Gaussian or like Redi quotients?
You mean usual?
Yeah, like localization.
Commutative range or something like that.
No, like the Redi quotient of category or like the Gaussian.
The roots? You mean the? I see. Directly, I'm not sure, but maybe some relation. So sorry.
No worries. Thank you.
Okay. So here's a localization property. So the main is, but the important is this has universality. So universality is if there exists other category satisfying these two conditions, invertible and isomorphic. So, but it's just a factor, just through this one. And also it has some good properties. So for example, this part just play a role of denominators in usual localizations. So this has such property, this kind of common values. And if T is abelian, so T tilde is also abelian or some good exactness here. So, but sorry, I need to go to next. So now we enter our main target. So first I define the determination modules in Hecke algebras. Okay, so this is defined. So first we define this one. This is a play a role of this Q factor here. Okay, so we consider the Fi tilde n on M is just this one. This is the head of the conversion product. Here we take Weyl group element W and red S. This is the reduced expression. And lambda be the dominant weight. So we define MK is this formula. So we saw some just before the similar one. Then the determination module is defined by this formula. So we apply this one according to this reduced expression on unit of the category. This is called determination modules. I'm not sure so why it's called determination modules, but so. And but I omit this one. So important point is this determination module is really has an affinization, and it admits it is real simple module and it admits an affinization. So then if we have affinizations, it has a good property. By the next here, so they are just the real commuting family of regulators. So Ci is if we take lambda be a fundamental weight. Lambda I is a fundamental weight, I fundamental weight. Okay. So using this, we can localize the category. So by using this localized one, we denote R tilde G. rgmod localized by Ci's. Then so this category categorified the so-called localized content-potent ring, quiver. So the expressed form of a quiver is as follows. So here's the definition of ref ring of quotient of R with respect to S. R is not necessarily a commutative. Then we consider the multiplicative set here, S here. Then the ref ring of quotient of R with respect to S is defined from property. Okay. Then so rgmod. It's a Grothendieck ring for rgmod is a ref ring of quotient of the ring. This is before, not localized, so original one, rgmod, Grothendieck for rgmod. This one is obtained by the multiplicative set of S is in this form. Then it has several good properties, but sorry, I don't have so much time, so I omitted these things. But number 4 is important because a simple object, any simple object in rgmod is presented in this form always. So this is the kind of the denominator. It's coming from the gamma. And also this one is from the original rgmod. So simple object in rgmod is obtained in this form. But of course this presentation is not unique. You know, the fraction is usually 3 over 6 is equal to 1 over 2, so it's, the presentation is not unique. So in this sense, this is not also, the presentation is not unique. So that's a problem to show everything. Okay. So the simple, self-dual simple module has a good property. So if we take a unique n, so just shift by q like this, then so it can be self-dual. If m is simple, then this can be self-dual simple. So now we take R inside rgmod, as it is self-dual simple modules. Then now we define the crystal structure on this family of simple modules. So the action of Fi tilde is really same as the Lauda-Vazirani's. So here Fi tilde action, this is simple part of original rgmod. And Ei tilde, we need some new part is here. So if Ei is not 0, so it's same as Lauda-Vazirani's action. But if it goes to 0, so we just borrow lambda I from here. Then applying a tilde on this, and then so we consider the conversion product, so then we can define the action tilde on this localization object. Okay. So this means so Fi tilde never goes to 0, but tilde also never goes to 0. So this action is free action. So I don't have so much time. So then the crystal structure weight and the epsilon the phi is defined like this. So it's really complicated for me. So anyway, so I show that this 6 tuple is a crystal. This is the first theorem. To show this one, so the problem is, as I said, well-definedness because this definition depends on the presentation. So we should show this definition doesn't depend on the presentation. So this is the problem. After that, so that this one is not so difficult to show that one. So the difficult point is why it is well defined. And next we just remember the cellular crystal. Here HI is the solution space of beta k's. Beta k equals zeros. Okay. Then so this vector this one 0, 0, 0 applying this one in here is really same as H lambda. This one. Okay. But this form is very similar to the definition of determinantial modules or where it is here. This definition. This definition and this definitions is very similar. Okay, so we just observe that category part determinantial module here. So using this determinantial module, we can localize the category. And also the crystal side, crystal base size, we have such object here, in here. And then so Lauda-Vazirani showed that rgmod K rgmod So observe these things. So we obtain the following result. Here we take the family of self-dual simple modules. Then we obtain the crystal structure here. Then we also have this one. S is just a simple object from here. And H lambda is just defined here. This one. So shift by this one. Then consider the or union. Then that recovers the BI, except the crystal. So this means this crystal is isomorphic to this one. Of course, here psi is obtained by Lauda. So the proof is, of course, complicated, and then the most difficult point is well-definedness. Indeed, so we have two presentations. So this isomorphism doesn't depend on the presentations. So that's a most difficult point. And after that, so bijectivity or some pressure weight drawn and commutativity of EIs and FIs are not so difficult. So the most important difficult problems. Then I have some problems, but so just time.